mathematical concepts from linear algebra, vector calculus, probability, and optimization to solve linear regression and other curve-fitting problems. In regression, we aim to find a function f that maps inputs x in Rd to corresponding function values f of x in R. We assume we're given a set of training inputs xn and corresponding noisy observations yn, which are equal to f of xn plus epsilon, where epsilon is an independently identically distributed random variable that describes the measurement or observation noise and potentially unmodeled processes. Throughout this chapter, we will assume zero mean Gaussian noise. Our task is to find a function that not only models the training data, but generalizes well to predicting function values at input locations that are not part of the training data. Illustration of such a regression problem is given. Regression setting is given in the left picture. For some input values xn, we observe noisy function values yn, which are equal to f of xn plus epsilon. To infer the function f that generated the data and generalizes well to function values at new input locations. A possible solution is given in the right figure, where we also show three distributions centered at the function values that represent the noise in the data. Regression is a fundamental problem in machine learning, and regression problems appear in a diverse range of research areas and applications, including time series analysis, control and robotics, optimization, deep learning applications, and classification algorithms. Finding a regression function requires solving a variety of problems, including each of the following: choice of model type and the parameterization of the regression function. Given a data set, what function classes, for example polynomials, are good candidates for modeling the data, and what particular parameterization, for example the degree of the polynomial, should we choose? Model selection allows us to compare various models to find the simplest model that explains the training data reasonably well. Finding good parameters. Having chosen a model of the regression function, how do we find good model parameters? Here, we will need to look at different loss or objective functions. They determine what a good fit is, and optimization algorithms that allow us to minimize this loss. Overfitting and model selection. Overfitting is a problem when the regression function fits the training data too well but does not generalize to unseen test data. Overfitting typically occurs if the underlying model or its parameterization is overly flexible and expressive. We will look at the underlying reasons and discuss ways to mitigate the effect of overfitting in the context of linear regression. The relationship between loss functions and parameter priors. Loss functions are often motivated and induced by probabilistic models. We will look at the connection between loss functions and the underlying prior assumptions that induce these losses. Finally, uncertainty modeling. In any practical setting, we have access to only a finite, potentially large amount of training data for selecting the model class and the corresponding parameters. Given that this finite amount of training data does not cover all possible scenarios, we may wish to describe the remaining parameter uncertainty to obtain a measure of confidence of the model's prediction at test time. The smaller the training set, the more important this uncertainty modeling is. Consistent modeling of uncertainty equips model predictions with confidence bounds. In the next video, we'll begin to discuss the formulation of a linear regression problem.